Welcome to the fourth Z80 programming tutorial for the ZX Spectrum. Now, it's essential that you have already watched tutorials 1 to 3 before commencing with this one, because we are in the middle of building a computer version of the Connect 4 board game. So at the end of the last tutorial, you had successfully programmed the O and P keys to move the counter left and right along the top of the board, getting ready for another key to be pressed to allow the player to drop the counter into the board. And that's the part that we're going to be covering today. It's quite complicated, but I've managed to successfully program it, and let's see how things go. So I'm pretty sure it's fairly easy to program a little routine that will drop the counter into the 6 slots and it'll come to rest at the bottom. So you just have to do a little loop that runs 6 times. But things get a little more complicated as you put more counters in, because it's not always going to be 6. It might be 5, it might be 2, or all the slots might be used up and you might not be able to put a counter into a particular column. So all of that needs covered in the logic of the program. So there's probably more than one way to do this, but the way that occurred to me was to set up a memory location in the fashion of a variable. I'm calling it drop, and I'm going to define 7 bytes, each with a starting value of 6. Why 6? 6 because there are 6 drop locations available in each of the 7 columns to start with, right? So for instance, let's say a player was positioned over the middle column, which is the 4th 6. This would be referenced as drop plus 3, by the way. So the first 6 can be referenced as drop. The second one would be drop plus 1. The third one would be drop plus 2, and so on. So that's how this array, if I can call it an array, you would call this an array in a high-level language. It's not really an array, but it kind of functions in the same way here in assembly language. So the word drop, just to let you know what's going on, the word drop just stands for a memory location. And let's take a wild guess. Let's say drop means 50,020. So that means the first 6 is in memory location 50,020. So the second 6 has to be in 50,021. So you see why the second 6 would be called drop plus 1. And the assembler has no problem with you writing it in exactly like that, drop plus 1, drop plus 4, or whatever. It'll just accept that and translate that for you into the relevant memory location that it will keep track of for you on your behalf. So I'm also going to create another pseudo variable called tDrop, and I'm going to start it with the value 0. tDrop is just my shorthand for temporary drop, and I'm using it as a temporary storage location for a piece of information that I need to put somewhere, because I can't just keep it in the accumulator, because I'm going to be using the accumulator, blah blah blah. It'll make sense a little bit later. It was just a convenience for me to create this temporary variable location that I could use. So when you see the code that we're going to create, you'll see how tDrop is used to overcome a particular hurdle. Okay, that's all the variables we need. So now we want to actually get down to the program. We want to enable the player to press the space bar. So in the same area of the program that you program the O and the P presses, you want to program the space bar, and the ASCII code for space is 32, so that's CP32. So it'll compare 32 with whatever was in the accumulator. So if it happens to be a space, we use JRZ, PFire. That will jump to a memory location called PFire that we are now going to create. I called it PFire just using arcade game conventions, player fire if you like. Here's how PFire begins. Okay, the routine that we need to create is quite complicated, but if you break it down into smaller problems, you'll find that they're all tackleable. They can all be done relatively easily. So the first problem, and this is the code that you're looking at that will solve that, is to make the player disappear from the screen. So it identifies the exact location of where the player is, and it changes the ink and the paper to white. That's what the value 63 means at the very end of that. You will see that the drop and t-drop variables are used. They're used to identify how many drops, how many squares the counter is supposed to drop, but it doesn't actually do anything with that data until the next section of code, which is following now. And there we begin by loading t-drop into the accumulator. T-drop will be 6 initially. LDBC, 32. 32 corresponds to the number of characters across the spectrum's display from left to right. So in other words, if you add 32 to the current attribute location, it will go across to the right, then it will jump to the next line, and then it will follow through until it is directly underneath your current square. So by adding 32 to the attributes, you go directly down one line. And when I reference PCall, the player color, I'm using PCall +1 because the original PCall variable related to the color against the white background. In other words, the player, as the player looks outside of the board itself. PCall +1 is the player color with the blue background that allows you to see the board. I'm using a halt instruction here. Halt waits for an interrupt. It simply has the effect of creating a very brief delay. And the reason I'm using that here in a tiny little loop called stall, that will repeat itself 5 times if you look at the variable, or sorry, if you look at the B register directly above, LDB, 5. So there will be 5 halt instructions, which creates a very brief delay, just long enough for me to be able to see the counter descending. Otherwise the counter descends far too fast. So this whole routine is DESND, short for descend. So each time it loops around descend, it goes one counter lower. And descend finishes depending on what was put in the t-drop variable. In other words, depending on how many drop slots are left. Following on from that then, we want to take one away from the slots remaining. You might think we should be able to do that with 1 or 2 instructions, but it's a little bit more complicated than that because we have to identify exactly which one of those drop locations that we have to change, whether it's drop, drop +1, drop +2, drop +3, etc. We can't just put something as complicated as drop plus pause. It's just too complex for assembly language, so we have to do it in a little bit more convoluted manner. And the last major thing you need to do is to change the color of the player. In other words, if the player was red, change him to yellow. If he was yellow, change him to red. The sort of logic that I am following here is I am adding 4 to the player color, and I'm also doing that for PCall and PCall +1 because I have to do it for the player with the white background and the player with the blue background. Yellow is always 4 greater than red. So I'm starting off by adding 4, but what if it's already yellow and it adds 4? Well, then you would get an invalid color, you would get the wrong color. But this I've actually accommodated this into the code. If you look further down, where it says CP18, Adding 4 to yellow creates an invalid color, and this CP18 notices that it's invalid, and it jumps to a little routine called BadColor, which will change the invalid color back to red again. So that's the kind of weird logic that I've followed with this routine. But it does work. It works quite effectively. And that's it. That basically completes our game. The only other thing I have done in my particular code is I have allowed the player to also press the R key when the game board is filled up or when somebody wins. So that was very handy. I'll not explain how that's done, but you'll see it in my completed code in the description. It's not very complicated, so it doesn't really need explanation. It's just a matter of resetting all of the color attributes within the board back to white ink with blue paper, and also resetting all the values of the drop locations back to 6. It was that simple. So if you're wondering whether the computer actually knows when you've got 4 in a row, obviously not. I'm sure, given time and experience, I could program a routine that would allow the computer to tell when a player has won. But that's some very complicated code, and I don't think it's a good idea to introduce that at this very early stage. Basically, what you have on your hands is the equivalent of the actual board game translated into the computer. So it's really up to the player to notice that he's got 4 in a row. And just like the original board game, you can restart the game at any point. So this completes Connect 4. I have placed a heavily commented version of the script in the description of this video. When you look at it, it may look quite messy, but that's just because YouTube doesn't show tabs in the correct place. If you highlight all of that code, copy and paste it into a text editor, you should find that the tab positions are preserved correctly and everything should look normal. So yeah, I think that completes our assembly language tutorial for the time being. I'm not sure whether there will be a part 5 at some point. Maybe I'll come back and do something about sprites or something like that, but for the time being, I think this is it. It was never my intention to create a tutorial series that would go on and explain assembly language at length. What I was really attempting to do here was just to help people who find it very, very difficult to engage with assembly language from the get-go, to take some of that initial confusion away. So I think I've been successful in that. And I have admittedly made a few mistakes along the way. I think in the first video I made the mistake of saying that the Spectrum's ROM could be temporarily overwritten. It can't. Someone corrected me on that. The ROM is the ROM. If it could be overwritten, it would be a PROM, programmable read-only memory, but it's not. It's just a regular ROM chip. I also said at one point that the DJNZ opcode affected the 0 flag. That's not true either. There have been a few other mistakes along the way. Also, my incorrect use of terminology, using words like compile instead of assemble. But nothing to get in a twist over. You really do need a full language reference guide, and there are many of those available. So yeah, good luck with your future programming projects, and I hope to see a lot of things produced for the brand new ZX Spectrum Next computer, which I can't wait to get come February 2018. Alright folks, thanks for your attention and hope this has been fun.